Hi, my name is Jeff Kurtz. I'm with Dirt Road Software, and I'm going to talk about a project I worked on a couple years ago that used event sourcing to deal with mobile device synchronization and consistency across mobile devices and web applications in a highly distributed environment. I'm going to show how the event sourcing approach allowed us to simplify the synchronization process and improve performance. So the project was at Wolters Kluwer Health. They have an application called UpToDate, and it's used by clinicians and medical practitioners to provide point of care support. It has calculators, graphics, medical topics, and the main application looks like this, with a search box for entering search terms, keywords. And below that is a feature that I worked on, which provided history and most viewed statistics, along with bookmarks. And this allowed users to personalize their experience and access information more readily. And I'm going to talk a little bit about the infrastructure behind UpToDate. And it consists of 5 data centers around the world, 2 in East Asia, 2 in the US, and 1 in Europe. The data centers provide locality of information so that users near the data centers can quickly access that data. And it also improves availability. In case one of the data centers goes down, users can be directed to a different data center. And the heart of the data centers is a central database and services that support those data centers, pushing information to those regions and also receiving information. The applications access the data centers via a global load balancer, and this keeps a health check on all of the data centers, and that will distribute load across the data centers in case one is not so healthy. It'll direct callers to a different data center, and if they take one out of load balancing to upgrade software, it will also direct traffic to those other data centers. The UpToDate applications consist of an Angular web application, a single-page app, and an Android and iOS mobile device. These are native applications. And the native applications, they also have local data storage. And so, as I mentioned, the project had to do with capturing history information for a logged-in user and bookmarks. And the initial concept was a profile document that would be shared across all the data centers and onto the mobile devices, and it would keep track of the history and bookmarks. And the initial thought was to use a distributed caching technology, and in this case they picked Couchbase document database, which supports replication across the various clusters, and was intended to quickly distribute the information. So if a user was connected to one data center and they updated their profile, it would automatically be replicated to the other data centers. And that way, if the user was directed by the global load balancer to a different data center, when they arrived at that data center, their profile would be there and waiting. So the technology, again, for this was going to be Couchbase. And so Couchbase, which we did end up using for the project, it's a document database, and it supports web, mobile, and IoT application scenarios. There are support for cloud deployments in Azure and AWS and Google Apps. And it has a memory-first architecture, so it's as soon as the documents are written into memory in a data node, they're available to callers. Actually, it's consistent in the face of partitions, network partitions. So if a node in the cluster goes down, the client applications will never receive stale data. They will always receive the original document if it's on a node that's still available, or it won't receive a document. There are replicas that increase availability, so you could refer to a replica in this situation. Multi-data center support in Couchbase allows documents to be replicated across clusters in different geographic locations or in different regions. And so that is designed to improve availability. Some other notes about Couchbase. The documents are stored as JSON, typically. You can do a key value lookup of those documents, and you can also do queries using the SQL extension Nickel that will allow you to access our query attributes of documents. And there's an indexing, global secondary indexing support as well. So as I said, the initial plan was to create a single profile document that would be shared and disseminated across all the data centers. And so let's just take the view of this document as the history document. So this document would maintain the content views that a user has throughout while they use the application. So they're looking at medical topics and graphics and calculators and other things. They would be, the application would record those as content views. And so here some of the attributes of a content view are the content ID, the time when the user viewed it, the count, the frequency of how frequently the content was viewed, and the type. So this example here shows a medical content view, and this shows a graphic content view, and this shows a calculator content view. And as the user kind of continues using the application, they may view these content items multiple times. So for example, the medical topic is viewed again and again, and then the calculator is viewed again. So from this, we have a domain object that consists of the history of the interactions that the user has had with the application. And there's different ways to look at that. We could look at it organized by recently viewed items. So the calculator was the last content that was viewed. And we can look at it through frequently viewed. And these are just different views of the same domain object. And we could write a service that would provide the ability to query that domain object in this fashion. So some benefits to the single document approach, and this is where a single document would be replicated across all data centers and would contain the entire history that the user's entire content viewing history. The single document has many benefits. It's easy to locate. So for a particular user, you could just say, give it an ID that consists of the user ID and the history, word history or bookmarks, and you could immediately retrieve them. It also provides quick summaries with Couchbase indexes, so you can create an index that's based off the contents of a document. So that's helpful, but there are some drawbacks. The anticipated content viewing for a year per user was about 250 content views, and so you can imagine the document growing each year by about 250, and then the next year another 250, and after that it's growing. So there's a concern about the document size, but there's also a concern about synchronization with the mobile devices. That document has to be passed back and forth, or a digest of the document has to be passed back and forth so that the mobile devices can update their local copy, or they need to download the entire thing and replace the existing one. There's also potential for lost updates from within a single data center. You might have multiple threads updating the document, so you have to control for that, and that's doable with Couchbase. But then there's across data centers. There's no global lock or synchronization mechanism across data centers, so you have to expect some data loss because of a conflict resolution. One of the documents, either the last one that was updated or the one that was the most updates, will become the document that gets replicated across all the data centers. And so there's a potential for data loss. And so it's these drawbacks that kind of led us down the path of event sourcing, because we were concerned about data loss, we were concerned about synchronizing with mobile devices, and we also worried about slower performance with a large document. And so we decided to use event sourcing, which we store the changes to the domain object rather than the domain object itself. And so the changes we call events, and they describe how the object changed, and they are indisputable operations that happened in the past. So in the case of history, the event we saved is content viewed. For bookmarks, the events are bookmark added and bookmark deleted. And once we have those events, we can replay them to recreate that domain object, or we can also create some indexes to do queries across those, just as we did in the single document example that I mentioned. And so what I'm going to describe next is the event log that we created to implement the event sourcing. And the event log is all the events of a particular type for a user. So there's a history event log for a user and a bookmark event log for that user. So let's first consider the case of a single event log for one user connected to one data center. And this is just so we can delay the discussion about replication of the event log across data centers. So here we have the domain object that we've seen before. It has three types of content that were viewed, their counts, and keep track of the latest time. And what we're going to do is we're going to replace the medical topics with the 3 topic views. So 3 content viewed events. And then the calculator was viewed twice, so we have 2 events for that. And the image was viewed once, so we have 1 image for that. And you might, since these all have timestamps for when the content was viewed, you could sort them and organize them by time. So the medical topic was viewed first, and the calculator was viewed most recently. Now, when we're saving these events, we didn't want to slow down the applications that were reporting that these events happened, so we used a message broker that stored them asynchronously. So it queued up events to be saved, and then they would save it to the database. Now, as you save them, since you're not guaranteeing that they get saved every time, the first time that we try to save them, it's possible that they're saved out of order. But in any case, when we save them, we do want to be able to identify them so that we can retrieve them later. So we're going to add a sequence number to each event. And so you'll see it's event 1, event 2, event 3, and 4 is not in time order, is not after event 3, but event 5 comes before event 4. And so this just demonstrates that the sequence of when things are recorded might differ from the temporal sequence. But it's these sequence numbers that are very valuable, because by having these sequence numbers, and these numbers are not duplicated, so only one event in this data center will have a sequence number of 1, 2, 3, 4, 5, and 6. And so we're guaranteed there's no duplication. So we can, when we need to retrieve the events in the event log, we can say, give us all the events with sequence numbers 1 through 6. Now, how do you know that 6 is the max sequence number? Well, we keep track of that in a separate document. That's the activity document. And this is a counter that gets incremented in an atomic fashion. Callers that are incrementing the counter will never receive the same number. And once they get that number, they use that to save and persist the document. All right, so now let's get into replicating the event log. So this is the event log, let's say for one data center. Let's say it's in the blue data center. So the application, when it was reporting that the medical topic was viewed or the image was viewed, it was talking to the blue data center, the service there. And that's why we're marking them as blue. Now, if another data center, as I mentioned before, there were 4 other data centers, but they were set up to support replication between data centers. So these events that are created in this data center within less than a second will appear in all the other data centers. So they are replicated as is to the other data centers. Now, if, say, the user is using the Angular application and the global load balancer directs them to the red data center, then they view some content, then you'll see new content view events that are recorded in that data center. And then there's a corresponding activity document that is for the red data center. And then, since we have replication, this will replicate over to the other data center. But because there's no guarantee of when things get replicated or the speed with which they get replicated, it's possible that the state of one data center will look slightly different from another data center. So in this case, we have the first event from the red data center is in flight. And so if the user was directed back to the blue data center, it's possible that they might not see the effects of this event because it's in flight. So if there's any a counter for most frequently viewed, it might be off because this has not propagated yet. This is a replicated event log. So all the events for a single user that are recorded in up to 5 different web forms are all replicated across all web forms. And so you can imagine that the other three data centers have exactly the same or very similar sets of events. In case that user, like I said, is directed over to that data center, you want that data to be there. Okay, so the mobile devices, they would periodically check to see if there are new events that need to be pulled down to the application. And the mobile devices were doing this so they could maintain a read model. And that read model is based off a replaying of events. So here's a graphic showing 2 data centers with 2 different devices talking to different data centers. And they have a read model that is being maintained on each device. This could be a user who is at a hospital moving from device to device. So it's like a shared device and they're logging in on the Android device and then they walk over to another part of the hospital and they're logged into an iOS device. And it just happens that each one is connected to a different data center, which can happen very easily. But this would be one user's view because these are all the events for a single user that I'm showing here. So let's just look at the request events and the receive events process. And so here we see the Android device, and it's sending this object here, as we call it, a sync object. And this object is a checkpointing object. So the previous call that was made by this Android device to get events, it returned this sync object. And that was telling the Android device in an opaque way. It doesn't have to know that it's at this value or what the value is. But it's a synchronization object that is used by the device to send on the subsequent request. And that will tell the data center where in the event log that user is, or that device is. And so the last event that Android device saw was event 2 in the blue data center. Okay, so that goes in, and so the data center then says, well, you've seen up to 2. Let me give you everything else after that. Using the activity documents, it figures out, okay, I got up to 3, 4, 5, 6 here, and 2. So I'm going to send those back to you. Okay, but like I said before, there's a sync object that comes back with these events. And that sync object in this case tells us that the max sequence number was 6 for the blue events and 2 for the red events. Okay, but what about the first event from the red data center? So we have 2 here. We know that that's a max of 2, but we don't have event 1. So in order to keep track of that so that subsequent calls will try to fill that gap, we keep track of gap ranges. So in this case, it's from 1 to 1. There's a gap. If the max sequence number in the red data center was up to 8, then you would also see a gap from 3 to 8. That has not replicated. And that would be a case where those events haven't replicated, but the activity document did replicate. All right, so let's talk briefly about performance stats. So event retrieval for mobile read model takes about 10 to 50 milliseconds. So that's what happens every 30 seconds, the devices connect to the service in the data center and ask for any new events. The recently viewed and frequently viewed queries, those are used in the Angular app, and those run when you click on the history view or the most viewed tabs. And they take about 100 to 250 milliseconds, and that's because they use the index service. So we index the information so that we can access it through a nickel query. And bookmark read model build, so if you ever asked to see your bookmarks in the Angular app, it took about 50 milliseconds to fetch and rebuild those. There weren't that many bookmarks. And event replication in data centers, I think I mentioned that, takes less than a second. Okay, so it did get tricky when we decided to support clearing history. So it was just as you would with your web browser, you would go in and clear history. We needed the ability to clear history in the UpToDate application. And when we did that, we didn't want to lose some of the statistics. So we didn't want to delete any events. And so we treated the history clearing as a kind of establishing a new cursor or a new lower bound for the event log. We have to establish a new lower bound so that we're not fetching the entire event log. We want to take a shortcut. We know that those older ones are no longer relevant. And so we would keep track of the new lower bound. And that was another piece of information that we stored in the activity document. So along with the max sequence number for the history events, we also keep track of clear history state information, which established a new lower bound. And if you clear history multiple times, it might be that you do it, that event is recorded in different data centers. And so clear history states would be created in the data center where the delete happened. So when you're establishing a new lower bound, you need to look at all the clear history states and pick the one that happened most recently and use that as your starting point. All right. And it got even trickier when we started deleting history. So there was a concern that the events would take up too much space in the database, and so we needed to delete them. Either the policy was to delete events older than a year, or if the user has more than 3,000 events, which is usually a sign that someone might be abusing the account, we would delete events so that they stay below 3,000 events. And so to do that, it's similar to the clear, except when you do a delete, we actually did delete the documents, and so they weren't factored into the frequently viewed statistics any longer. Now, since deleting events is permanent, and there's no way to retrieve those documents after deleted, we had to keep track of the items that were deleted, things that had a higher sequence number than the new lower bound established by the delete. Otherwise, we would continually check to see if the items were available. And so if we knew things were deleted, we could know that there was no reason to try to retrieve them again. And something I forgot to mention earlier was that anytime you're describing missing information, so these are deleted events, or it's possible that there's gaps in the event log, you want to put a timestamp on it, on those gaps or those ranges, so that the application knows to stop trying to fill them. So for deleted, it was not necessary, but for the gaps that a data center was not aware of certain events, and the sync state was returned with a gap range, it's possible that there was a partition prevented connectivity to one of the data centers, and so replication had stopped, either because it was a crash or because it was taken offline. And so we set when to stop, filling the gap to 3 days. So we figured that the partition would heal or be fixed within 3 days. And so that if anything had to be replicated to fill in those gaps, it would happen at that point. So here's some statistics on Couchbase. So for a single data center, the statistics, there was about 300 million documents. And that was all the content view documents, the bookmark documents, and activity documents. The data size was about 230 gigabytes, and that was split across 3 nodes. The index size was 140 gigabytes, and the data service consists of 3 nodes, and the index query services were on 2 nodes, so it was a total of 5 nodes per cluster. The complete deployment, which included a backup and reporting cluster, gave us 6 clusters with a total of 27 nodes. And so just to summarize, so the event sourcing approach helped with avoiding lost updates. So we were able to provide consistency as the user moved from data center to data center. We separated logs by location and then merged to create views or read models. And that was important for avoiding data loss. And we had to plan for eventual consistency. So all the applications knew that the events weren't always available at all times. We also facilitated fast read model updates in the mobile devices using our synchronization mechanism. And if you want to find out some more on this approach, Martin Krasser's ACA persistent-based solution is a library that supports this approach with a distributed event log. I believe it is open source, and there's a study of convergent and cumulative replicated data types that talks a lot about the eventual consistency and different guarantees that can be made in light of replicated data. And for a single cluster event store, which is a high-performing event store is eventstore.org. And if you look back at some of the Boston Secure SES meetup presentations, you can find his presentation. All right, and feel free to reach out to me at jeff@dirtroadsoftware.com. Thanks.